Hey everybody, this next video lesson is going to talk about predicting products of some common chemical reactions. The FRQ section of our test coming up here in a few weeks is going to have a couple of chemical reactions in word form that you're going to have to figure out how to translate from words to symbols and then also predict the products. So I'm going to show you a couple of reaction mechanisms, which is basically how to carry out the reaction, and also some keywords to look for to help you identify what type of reaction you're looking at. So there's a lot of different information that's about to come at you, so hopefully you can consume it all in an efficient manner. But we'll start here with identifying the four types of reactions that I'm going to be talking about. The first one we're going to talk about is single displacement, and there's multiple different types of single displacement, including halogen replacement and hydrogen displacement. We're going to talk about synthesis, decomposition, and combustion. Now all four of these, as we mentioned in the last video lesson, are examples of redox reactions. Not only are they redox reactions, but you'll be expected to know how the reaction is carried out. So let's first start talking about just a general single displacement reaction, where you have A, which is usually a metal, reacting with an aqueous solution we'll call BC. Now in order to determine if A is going to kick B out, we need to figure out if A is more reactive than B on the reactivity series. If A is higher than B on the reactivity series, then A will replace B. But if the opposite is true, if B is higher than A on the activity series, then this reaction will not occur. The list you see over here on the left is a list of elements, and the list of elements is ordered from top to bottom in order of most likely to get oxidized. Remember, the term oxidize means likely to become an ion. So these elements are more stable in their ionic form than they are in their elemental form. We also refer to these elements as strong reducers. A reducer is something that gets oxidized. A reducer means that it does some oxidation. So it doesn't get reduced. Reducers get oxidized. Now as you go down the list, you become less and less of a strong reducer, and you become a weaker reducer. And weak reducers are more likely to get reduced. And if something gets reduced, it really, in other words, becomes a metal in a single displacement sort of type of reaction. So weak reducers are more stable as neutral elements, where strong reducers are more stable as ions. Here's an example of a single displacement reaction of iron, metal, and I know it's metal because when it's by itself, it always exists as a metal. And it's in a solution of copper 2 chloride. So I'm going to write aqueous here. Now this reaction, first of all, I need to determine whether or not the reaction is going to happen. So I look for iron, and it's above copper, so it will happen. So if I predict the products, what I get is copper now by itself, because if it's lower on the table, it's more stable as a neutral element. So copper is by itself, and iron now is with chlorine. Now iron, I didn't identify what oxidation state it would become, so you get to pick. Iron is a +2 or a +3, and if you choose +2, then it's FeCl2. Now on the quiz or a test, I would probably say, like +2 up here, saying if this reaction did happen, it will become a +2 charge oxidation state. Now, oftentimes, when you read a reaction, it could be one of many different types of reactions. So you look at the wording of the question, you also look at the symbols or the elements involved to decide what type of reaction you're working with. And single displacement reactions always have like a metal dissolved in something. So look for the word metal, or a solid dissolved in an aqueous solution, or just a metal mixing with an aqueous solution. Other keywords that you know are going to be a single displacement reaction are the words oxidize and reduce, because single displacement are redox reactions. So if you look for the word oxidize or reduce in the sentence, it's probably a single displacement, as long as what's being oxidized and what's being reduced is a metal, or what's being reduced is a metal. Now there's a special type of single displacement called halogen replacement, and this is a single displacement where halogens replace other halogens in a single displacement sort of scenario. There is no published activity series for halogens displacement because it is based on the order in which they occur on the periodic table. The higher up on the table, the more likely it is to replace something below it. So fluorine being the top will replace anything below it. Chlorine will replace anything below it, but not fluorine. An example of a halogen replacement is something like this. So you have a gas, like fluorine gas, bubbled through an aqueous solution. And that's the wording that you'll look for. Some gas being bubbled into a solution. Oftentimes, if something's being bubbled into a solution, it's either trying to be a single displacement scenario or a synthesis scenario. And in this case, it's a single displacement because what's being bubbled is a halogen. So look for a halogen gas being bubbled through a solution. Now the halogen is going to replace the halogen in the solution. In this case, the bromine is the other halogen. And since fluorine is above bromine in the activity series, that means that bromine is going to be by itself, and that's going to come out in its natural state, which is a liquid, and copper is going to be with fluorine now. Now copper is not going to change its oxidation state. It started out as a +2 on this side, so it'll remain a +2 on the product side. Now the state of matter doesn't really matter. You're not graded on labeling the states of matter, so it's okay if you didn't know that bromine is a liquid at room temperature, but I just wanted to mention that. Now if I rewrite this reaction as a net ionic, taking into account that copper is +2 charge aqueous on both the reactant side and product side, I can kind of skip over the full ionic scenario and just cross it out of the full reaction and rewrite it as its net ionic reaction F2 plus Br minus, but there are 2 of those ions, so you pull out the 2 here in front. And then you end up with Br2 and then 2 F minus ions. And that is the result of the F2 being broken down into its individual ions. And this is the net ionic reaction for this halogen replacement. Here's an example of a type of problem that you'd be expected to answer on an FRQ portion of a test for this chapter. Now I will mention that the FRQs that pertain to chemical reactions on the AP test outside of this chapter are actually just usually sprinkled in as part of a 10-point question or a small part of a 4-point question. So on the actual AP test, there's no dedicated section for chemical reactions. It's just assumed that they're going to be part of other larger types of problems. But this is something that you might see as part of a larger type of problem. So the wording here says that chlorine gas is bubbled through a solution containing potassium bromide. So the clues that I'm looking for here is that there's some gas being bubbled and that there's a solution of potassium bromide. Now, of course, I told you we're talking about halogen replacement here, but those are the clues that you look for if you're just walking up to a problem with no idea what the problem is actually trying to get to. You look for these clues in the words. Gas being bubbled through a solution. Now, we need to identify the net ionic, but before we can do that, we need to identify the full ionic and figure out what is being spectator and what's actually being reacted. So chlorine gas, I start with the Cl2, and you can include the state of matter, but you don't have to, is being bubbled through a solution of potassium bromide. K is a +1, bromide's a -1, so K, Br, and it's a solution, so it's aqueous. Now, chlorine is above bromine on the activity series of halogens, and so it will replace. Bromine then is going to be by itself, and it's going to be a liquid, but you don't need to include states of matter in your answer. And then, of course, the K is going to be then with the Cl. Now, you can balance this now or later. I'll balance it now because it's pretty easy. But if you double the chlorine on the right, and then you double the bromine and the potassium on the left, you have a balance of 1, 2, 1, 2. Now I need to split this up into the full ionic and then eliminate the spectator and finally have the net ionic. So here's the full ionic. In red, I've got Cl2, I've got 2 potassium ions because it's 2 times K and 2 times Br, and then I've got 1 bromine and then 2 Ks and 2 Cls. And now I go in with a different color and I eliminate anything that's equally abundant on both sides of the reaction. And you've got 2 potassium ions on both sides, and those have eliminated. Now I rewrite this with those 2 eliminated, and you get the net ionic reaction. And once you clean it all up, this is what you have in blue. This is the net ionic reaction for this halogen replacement. This is another type of special single displacement. They identified as hydrogen displacement. And what you're looking for is a metal and water or an acid are your 2 reactants. Have a chunk of metal in water or a chunk of metal in acid, and I identified an acid just as HA here. This could be any acid, starting with a hydrogen and any anion. Typically what you'll find are alkali metals or alkaline earth metals, and these metals can displace hydrogen in water or an acid, and H2 usually bubbles off and catches fire as a result. So in any of these problems, when you see a chunk of metal or a metal oxide, for example like Na2O, when you add that to water, the resulting compound will always result in the metal hydroxide and hydrogen gas. The hydroxide would be aqueous and the H2 will just bubble off. If the temperature or heat is high enough, the H will actually start on fire. As far as translating to net ionic, usually these hydrogen displacement reactions, the full reaction is the net ionic reaction because there are no spectator ions. There's nothing aqueous to start. You have a solid and a liquid. And then the products are a gas and aqueous. So you only eliminate it from the full reaction if it's aqueous on both the reactant side and product side, but there is no aqueous on the reactant side, and so you don't need to worry about it. Now if the reactant was acid, the anion of the acid would act as a spectator. Here's a reaction of sodium with hydrochloric acid. Now the sodium starts out as a metal, and the hydrogen is a plus and the Cl is a minus. The Na is a plus and the Cl is a minus on the product side, and then H2 gas as a result. If I cross out the substance that is both ionic on the left side and the right side, it's the anion of the acid, and the resulting net ionic reaction will have just Na plus H plus, and then the cation sodium dissolved into the acid plus the H2 gas bubbled off. So the stuff that I circled wouldn't be included in the net ionic equation, but the spectator ion would be the anion of the acid. But going back, adding a metal or metal oxide to water alone will result in a metal hydroxide and hydrogen gas. So these two products are always a result of something dropped in water. But if you drop it in acid, you need to figure out the net ionic. But in both cases, hydrogen is one of the products, and thus it's called hydrogen displacement. The next type of reaction that I want to talk about is synthesis. In a synthesis reaction, we have the absorption of a gas by a pure element or compound. So usually that pure element is going to be a metal of some sort, and the gas is usually like O2 or CO2 or some sort of gas in the atmosphere. In this situation, you take the metal and the gas, and they usually combine in a 1-to-1 ratio. Now it's worth pointing out that it doesn't have to be a pure metal. It could be a compound. Like the example we have down here, the compound magnesium oxide would combine with carbon dioxide in the atmosphere to create magnesium carbonate. That is a 1-to-1 ratio, and if it doesn't balance 1-to-1, then it's not considered a gas absorption. So when you're reading a problem in an FRQ, what you look for is the keyword gas absorbed, or something is synthesized together, something like that. Sometimes the word synthesis will be in the wording of the question, or you look for the word absorbed or combined. So if you see the words absorbed or combined in the problem, it's probably a synthesis, gas absorption, where you just take the two elements or compounds, you put them together, and the resulting compound is a 1-to-1 ratio. Next, we're going to talk about decomposition reactions. And you see a large list of different types of compounds that could result in a decomposition. But I've highlighted a couple here by starring them. And it's the carbonates, the sulfates, the chlorates, and the metal oxides. In a problem that has a decomposition situation, there's only one reactant. And oftentimes, the wording of the question says something like it's heated up, or heated to decompose, or is broken down into, something like that. So look for that key word when you're identifying a decomposition reaction. I'm only going to test you on these 4. I know this is a lot to consume when it comes to identifying the different types of reactions and the different mechanisms, but I think it's pretty fair that I cut this large list down into just a couple. So any carbonate that you see will be heated or decomposed into the oxide, the metal oxide, and carbon dioxide. Sometimes it says it's aqueous, but really carbon dioxide will be as a gas. Now, the sulfates that you'll see will be broken down into a metal oxide and SO3 or sulfur trioxide gas. Any chlorate gets decomposed and you get the metal chloride and the oxygen gas. And finally, any metal oxide that gets decomposed will break down into its metal and O2 gas. So my suggestion for decomposition is to try and make a couple of flashcards to help you remember, because the tough part about decomposition is sometimes they break down one way and then you switch the substance and it breaks down a different way. And it's best if you just make a couple flashcards to help you remember these. But any decomposition reaction I use on the upcoming test will come from these 4 that I've starred. Now I realize after proofreading my video that there's a little bit of scratchiness on this particular slide, and I apologize for that. I think it was because my microphone was rubbing up against my shirt or something while I was recording, but I'm not going to re-record this slide. I'm sorry, and I hope you can forgive me. And finally, the last type of reaction is the combustion reaction. Now, most combustion reactions are pretty straightforward. It's got a carbon-containing compound and reacts with oxygen to produce carbon dioxide and water. But that fuel doesn't always have to be just carbon and hydrogen. It could be an alcohol, and an alcohol has an OH in it. So like methanol is CH3OH. That could be a legitimately used fuel. Or any other large macromolecule hydrocarbon like sugars, C12H22O11. This could be burned in the presence of oxygen to produce carbon dioxide and water, just like any of these other carbon-containing substances. And the last little note on this combustion slide is this, that combustion of any element in the presence of oxygen will always produce an oxide of that substance. So let's think of a Venn diagram for a second. Over here, we have all synthesis. And over here, we have all combustion reactions. And right in the middle, we have this situation where any element is burnt in the presence of oxygen will produce the metal oxide. These types of substances are both synthesis and combustion type reactions. Anyway, that's a lot of information to consume. We went over all those different types of reactions and what to look for in order to do some FRQs. Hopefully, you picked up some stuff. You might need to watch it a couple times in order to get it all down. Or pause, rewatch, take some notes, make some flashcards. Anyway, that takes care of this video lesson. Thanks for watching.